Welcome to Unit 11, Section 2, the definite integral. And in this section, we're going to revisit the idea of the area underneath of a curve or underneath a function. And when we first looked at that, we found that the area underneath a curve could be found by using Riemann's sum approximations and using rectangles and finding the area of rectangles and summing those together to get an approximate area. And we also looked at the limit of the Riemann sum as the rectangle width or the subinterval width approached zero, and how that limit gave us an exact value for the area underneath of a curve. And so we're going to continue to look at that idea of the limit of the Riemann sum as the area, but we're going to redefine it and call it a definite integral. And so we say the definite integral of f of x over a to b is denoted by the integral sign and is the limit of the Riemann sums. And once again, we can use any Riemann sum in our limit, whichever one you want to choose, left, right, or midpoint. But if our endpoints are a and b, we use an integral sign just like we did in the indefinite integrals, but we're going to define where we start and where we end with a and b. And so if we integrate f of x over the interval a to b with respect to x, it is equal to that limit that we found back in last unit when we were approximating the area underneath the curve. And when this limit exists, we say that f of x is integrable over the interval a to b. Now, if f of x is a continuous function, then we say that it's integrable over that interval a to b. But also, if it's at most has finitely many jump discontinuities, then we can say it's also integrable over the interval. And let me explain what that means. Obviously, if we have a function that's continuous, we can find the area under the curve. Well, if we have a function that is discontinuous, say something like this, and there's an open circle here, and we have an open circle there, and so we have a point of discontinuity, or even, let's just say it's closed, that's fine. We have a point of discontinuity, but since it's a jump discontinuity, we just go from one y value to another, we can still find the area underneath the curve here. All right, so we can still integrate along that function, whereas we would not be able to integrate a function such that we had a vertical asymptote here and we wanted to integrate from here to here. Well, since these go on forever, we can't find the area because the area goes on forever and ever and is infinite. Okay, so jump discontinuity, we're okay. Discontinuity like this, where the limit goes off to infinity, not okay. Okay, well, let's talk about the area. And area is a positive quantity by nature. Okay, there's no such thing as a negative area. You can't find the area of a surface and say that it's negative. However, in calculus, we will give signs to certain areas depending on where they are relative to the x-axis. So we say any area above the x-axis, such as this area here, we call positive area because it's in the positive range for y. So positive area above the x-axis, area that is below the x-axis, we call negative area. The area itself is positive because all area is positive, but we denote the area as having a negative sign. It's a negatively signed area. And so by doing this, we can say the integral of any function f of x from some point a to b is always going to equal the signed area of the region between the graph and the x-axis over a to b. So if we wanted to integrate this function from a to b, we simply add these two areas together, giving the area underneath the x-axis a negative sign. Okay, now at this point, we're going to have to resort to using geometry to calculate our area. When we get into the fundamental theorem of calculus, we're going to have another technique that will help us deal with more difficult functions. But for right now, we're going to use geometry to calculate our area. So let's take a look at two different functions that are very similar, but a little different here. Let's look at the function 3 minus x and the function, the absolute value of the quantity 3 minus x. And let's look at the definite integral from 0 to 5. So if we're going to integrate these two from 0 to 5, we can look at these graphically. Now, this is a line. Our first function, 3 minus x, is a line, and so we're going to expect to see triangles here. Well, the absolute value of the quantity 3 minus x is also a linear function, but it can be expressed as a piecewise linear function in that it won't dip below the x-axis. It's going to remain positive. So if we look at these two graphs and we examine them, we see that for our first function from 0 to 5, we have positively signed area and we have negatively signed area. So this positively signed area has an area of 9/2, and we get that from using geometry, 1/2 base times height. And this area, this triangle, has a negative area, or negatively signed area, of -2, once again using geometry. So this integral from 0 to 5 is simply the sum of these two areas, 9/2 and -2. And so we can say that this definite integral, this function from 0 to 5, has a total overall area of 5/2. Whereas if we look at this area over here, for the absolute value of the quantity 3 minus x, we still have that positive area of 9/2, but this area is now positive because it's above the x-axis and it has an area of 2. Still an area of 2, but now it's positive 2 instead of -2. And so this integral is 9/2 plus 2, which gives us 13/2. So we can look at these two functions that are very similar, but the function 3 minus x and the absolute value of that function give us two different areas. Okay, so when we integrate even over the same interval, we get two different areas because in the original function 3 minus x, we have a portion of that area below the x-axis, which gets a negative sign. One last thing to look at here is, what if we have a constant? And if our function is just equal to some constant c, that graph is a horizontal line. And say we want to find the area under the curve from A to B, well, the shape is simply a rectangle with one dimension c and the other dimension b minus a. So to find this area, we simply have to multiply those two quantities together, which tells us that the integral from a to b of a constant with respect to x is simply that constant times the difference between b and a. So an example of this is if we wanted to integrate from, say, 1 to 3 of 6 dx, well, that would simply be 6 times 3 minus 1. Well, that area is 12.